Okay. Okay, so we were looking at two motivations for looking at pseudo-randomness for cryptographic applications, but also for de-randomization of algorithms. So, so let's look at, so the second part of the talk is going to concentrate on pseudo-random generators and de-randomization of algorithms. Okay. So, when we want to talk about when we can simulate a probabilistic algorithm deterministically, we have to talk about what a probabilistic algorithm is. And if you think back to all the examples that we looked at the beginning, the algorithm had some input and then made a sequence of random choices. So we can think of, and from then on it was deterministic computation as normal. So we can think of a probabilistic algorithm as having a real input and then a secondary input, which is list of random choices. Okay. So so we'll think of the algorithm A as having input X and random choices R, and then we have to say, well, now for each input, instead of a hard and fast yes/no answer, there's a probability of a yes answer, a probability of a no answer. So how do we map that to yes and no? So we don't, if it's ambiguous, if it's 50.001% chance of saying yes and 49.9999 chance of saying no, okay, then we'd have to run the algorithm a huge number of times before we even observe the difference between yeses and nos. Okay? So there isn't a clear, unambiguous answer. Somewhat arbitrarily, we usually pick 2/3 as our criteria for when the answer is unambiguously yes or unambiguously no. Okay? Now, even when you put that proviso, there are two ways of modeling what it means to de-randomize all probabilistic algorithms, or how to define the class of probabilistic algorithms. So BPP, for bounded error probabilistic polynomial time, puts the onus on the algorithm designer. Okay, says on every input, your algorithm only counts if on every input it's unambiguously yes when the answer is yes, and unambiguously no when the answer is no. Okay, so a more robust notion, so if X is in L, the algorithm should accept with probability 2/3. If X is not in L, then it should reject with probability 2/3. Okay. A more robust notion of simulating, so then we could simulate probabilistic polynomial time if P equals BPP. Okay. A more robust way of saying we can simulate probabilistic polynomial time is the class promise BPP. There, the onus is on the simulator rather than on the probabilistic algorithm. So promise BPP captures a lot of situations like using randomized heuristics, which sometimes have an unambiguous answer and other times are murky. Okay? So to simulate a promise BPP algorithm says when, or a promise BPP problem says when a probabilistic algorithm says yes with probability 2/3, you, the deterministic simulator, have to say yes. When it says no with probability 2/3, you, the deterministic simulator, have to say no. And then I'll give you the freedom when that promise isn't kept that the probabilistic algorithm is unambiguously yes or no. If it's murky, you can say either one. Okay. And so promise BPP, things to be in BPP have to have a lot of structure usually. Okay. But promise BPP allows kind of unstructured heuristic use of randomness. Okay. So okay. So Yao, in that paper, the second paper on cryptographic pseudorandom generators, also observed that they could be used for de-randomization. If you can minimize the amount of randomness, you can then do exhaustive search over the possible pseudo-random tapes and try each one, the randomized algorithm, using each one as its source of randomness. Okay? And so the overhead is exponential in the number of possible, in the amount of randomness that you use in your generator. Okay? So now, in order to make this work, he had to define security. We said in cryptographic security there are two possible ways of modeling the adversary: as a probabilistic polynomial time machine or as a polynomial-sized circuit family. What's the difference? A circuit family is a non-uniform model of computation. So in both, for every input length, you have to have an attacker. Okay, and the attacker has resources polynomial in that input size. Okay. In the non-uniform model, the attacker's method can be different for every length. So you optimize, or in other words, you sort of can, in a polynomial-sized circuit, if you've got an exponential family of possible attacks, each of which, though, once you write it down, can be implemented in polynomial time, the attacker can take the best one of this exponential size family. Okay? Whereas in the uniform model, the attacker has to be able to come up with its strategy in polynomial time, not just carry it out in polynomial time. Okay? This is important when you're de-randomizing algorithms in the worst case, in that the simulation by the pseudo-random generator might fail on some just very peculiar inputs, might work for almost all inputs, but fail on some peculiar, hard-to-find inputs. And those would be the code for the non-uniform attack on the algorithm. So at least the obvious proofs that pseudo-random generators allow you to de-randomize algorithms require security versus these non-uniform attackers. Okay. But other than that, it goes through as follows. And so if you've got a pseudo-random generator versus, in the cryptographic sense, versus circuits, versus polynomial-sized circuits, then you can simulate even promised BPP algorithms in deterministic time sub-exponential, 2 to the n to the delta for an or 2 to the n to the epsilon for an arbitrarily small constant epsilon. Okay. So, so you get non-trivial de-randomization of probabilistic algorithms. Okay. Oh, and on the high end, if you have a pseudo-random generator that's good against adversaries that run even in exponential time, then you could get an almost polynomial time, quasi-polynomial time simulation using the same method. Okay. So, the question is this very strong cryptographic one-way function, which is the cryptographic pseudo-random generator against this very powerful non-uniform adversary, is this really what we need to de-randomize algorithms? It seems kind of overkill. We're being paranoid about the powers of, the algorithm would only invert our pseudo-random generator accidentally. Would only break our pseudo-random generator accidentally. And here we're taking a pseudo-random generator that's sort of loaded for bear, is able to cope with very powerful adversaries that are intentionally trying to break it. So are we overshooting the mark with this kind of pseudo-random generator? So for example, I argued that you need a one-way function to have any kind of meaningful cryptography. Does that mean you actually need a one-way function for de-randomization? The argument doesn't follow through because you don't have an adversarial situation. Okay. And we have this kind of unusual thing where we needed hardness against non-uniform adversaries, against circuit families, to prove the de-randomization results. Can we get by with a weaker kind of uniform adversary? Okay. And maybe we can de-randomize, just because, the pseudo-random generator approach may not be the only way to de-randomize algorithms. In fact, there are a number of other approaches like the method of conditional expectations. So maybe we could de-randomize these algorithms, come up with deterministic versions of the algorithms without pseudo-random generators at all. Okay. So, if you think about it, the requirements for a pseudo-random generator to de-randomize an algorithm are quite different from the requirements that we needed for cryptographic applications. So, in the cryptographic applications, we're going to just pick a random seed, and we're going to use the generator on that seed, and and we're not going to consider any other random seed. Okay? But in the de-randomization, we're going to be doing, we just use the generator on a random seed as a conceptual tool. What we're actually going to be doing in the de-randomization is trying the algorithm on the entire range of the generator. Okay? So it's actually less important. That makes it less important because it makes the seed size much more important in some sense, but it makes the time that the generator takes, that we take to compute the generator, much less important because we're going to be using it an exponential number of times anyway, exponential in the seed length of the generator. Okay. Another thing is that in cryptography, we're using the good people are using this randomness in a way that's taking very little time, and yet we have to be secure against an attacker who could take potentially quite a bit more time. Okay? So maybe our protocols are linear time, but we need to be secure against an attacker that's taking n to the 100th time. Okay? In de-randomization, it works in our favor. Okay? If we're willing to have like some overhead. So if we're willing to take an algorithm that runs in n squared time and simulate it deterministically in n to the 4th time, okay, then we still only need to our generator could take n to the 4th time to compute, but we still would only need to be secure against the algorithm whose resources we know in advance is n squared. Okay. So instead of having to deal with security, an adversary that has more power than we have to deal with an adversary that has almost as much power as we have. And just come as close as possible. And the first people to really take advantage of these differences were Nissan and Wigderson, and then sort of a more complete program was given by Babai Fortnow, Nissan, and Wigderson. And it shows that if we've got a function, okay, doesn't have to be easy, so a one-way function had to be polynomial time computable. Here's a function, it just has to be exponential time computable. Okay? And it doesn't have to be hard on average to invert. It has to just be a Boolean function that you can't compute exactly, in the worst case, with polynomial size circuits. Okay? Then you get a pseudo-random generator that stretches n to the epsilon bits into n bits that fools any time n algorithm. And the pseudo-random generator isn't computable in polynomial time, it's computable in 2 to the n to the epsilon time. Okay? So if you put that together, if we've got this hard function, hard in the worst case, but against non-uniform adversaries, then we get a an algorithm, deterministic simulation of any probabilistic algorithm, promise BPP type algorithm in 2 to the n to the epsilon time. Okay? 2 to the n to the epsilon to compute the generator times 2 to the n to the epsilon to do exhaustive search over the keys times some negligible factor to simulate the algorithm on each once you have the pseudorandom source, pseudorandom string. Okay. Okay, and then with Avi, we got the following quantitative improvement. Said that if you've got a function that's exponentially, that's in E and exponential time computable and requires exponential size circuits, then you can de-randomize any probabilistic algorithm with polynomial overhead. So this is a nice clean statement of the result, cleaner than the previous slide, but it's just following the same outline as the previous slide, and I'm just going to give, as the previous results, and I'm just going to give the sketch for the BFNW technique and not go into details of how we got the quantitative improvement. Maybe I'll put this over here. But if you think of it, though, this result is somewhat remarkable in the following sense. Okay, what would happen if you look at the contrapositive of this statement? You say, if we can't simulate a probabilistic algorithm deterministically in polynomial time, then what happens? Then every function that's computable in exponential time has a sub-exponential size circuit family. That means that you can somehow condense computation by doing some sort of offline computation. You can, given any function that's computable in exponential time, there's some way of minimizing, computing the best circuit layout that shrinks the function, the size super polynomially over any obvious simulation of the algorithm. So I think it would be a pretty unlikely set of events, right? In that computation is compressible with offline work. So my conclusion is, I think that the negation of that clause in the if is just kind of ridiculous, much more far-fetched than, say, P equals NP. Okay. Well, even if P equals NP, then it's actually true. So it just seems that, what we should take away from this is that, in fact, randomized computation and deterministic computation are the same model of computation. It's just a matter of proving it now. Okay? So we already know the answer. Now prove it. Okay. Okay, so what is the BFNW approach to this kind of hardness-randomness trade-off? Okay, so there are 3 steps. The first 2 could be condensed, but I like to think of them as separate. Okay, so the first step is, and each of these steps has a very interesting combinatorial content that you can understand without, the complexity picture at all, in some sense. Okay. The first step is we go from worst case hardness of a function to significant average case hardness. So where we said that originally our assumption is just we can't have a circuit that's right all the time. Then we'll get another function where you can't have a circuit that's right, say, 99% of the time. Okay. So there's a good probability, polynomial probability, that the function is hard. Okay. Then we'll have the second stage is hardness amplification, where we take this hard, average case hard function and make it into a function where you can't even guess the answer on a random input with significantly more than a 50-50 guess. So that's kind of like what we were doing with the hardcore predicates of Goldreich and Levin, compressing things down to a single bit, okay, that looks random. Okay? And I want to say both the first steps, if you go back and think about what we're doing, these first two steps you can think of in the language of error-correcting codes very similarly to how we were thinking about the Goldreich-Levin hardcore bit as in terms of error-correcting codes. Okay. So then the last step is in some sense the most novel, okay, in that I'm still impressed by it. You have, after the second step, you have one bit that looks random. Now I should say that that bit is deterministically computed, but you have your input x and then your output h of x, and the given x, h of x looks random. What if we did the same construction as we did in the cryptographic case? Okay, took one bit and output it, and then used the other bit in the recursive in the rest in the recursive construction. Well, we would take h of x and output it, then x is random given h of x. We'd plug that back into the construction. What would we do? We would output h of x and plug x back into the construction, output h of x, plug x back into the construction, and repeat. We have two possible outputs we could get that way: 0, 0, 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1, 1, 1. Neither of which looks random. Okay? So it's no longer true that one additional bit is enough. In this context, it's really a challenge to go from one additional bit to many additional bits. Okay? So what we need are, and we don't have the luxury, since we need to keep that seed size very small, we don't have the luxury of picking many inputs x independently and outputting one bit, because still we need more bits, we need many times more bits of output than we have of input, and there we're taking like n bits of input and just getting one more bit of output for each n. Okay? So they do something remarkable, which is they say from a small amount of randomness, we'll generate many inputs to this function. These inputs are not at all independent because they're all based on the same small seed, but they're computationally independent in that knowing the bits on some of them don't help you compute the bits on the others. And the combinatorial basis, here they're using a pseudo-random combinatorial object called as a design to define these computationally independent inputs. Okay. So that's the outline, and let me put it up here. Okay, and then we'll go through the different stages. Okay, so here's the first step. Okay, say we've got any Boolean function on L bits that outputs one bit. This is our hard Boolean function. Okay, each function has a multilinear extension. Okay, a unique multilinear extension over some finite field, and we need the finite field to have more than L elements by some amount. So let's say L cubed elements is enough. Okay? So each of these elements of the field is describable by about log L bits. So we're increasing the size of the inputs a little. Okay? But not by a huge amount. Okay? And this new function, this multilinear extension, agrees with the old function when the inputs happen to be 0 and 1. The final thing is f hat can be computed from f, but with exponential time overhead. Okay? Now, so remember that, what's going to sit, this would be a killer in any kind of cryptographic context. We're taking exponential time in the input size to compute f hat. But remember, we just assume that f, in this context, we're just assuming we're going to be like doing exhaustive search over these inputs anyway. So 2 to the input size isn't going to be so bad. We're going to pick the input size very small. Okay. So, okay. You can also, from coding point of view, we'll see that actually there is no way actually of making the connection between f hat and f sub-exponential.
Even the field with the L cube elements.
Yeah.
Not 0.
Assume L cubed is a prime. It just has to be some field that has more than L cubed element. We don't want it to be too huge, and we don't want it to be too small. It doesn't have to be any particular size. So pick a prime, say between L cubed and 2L cubed. Sorry. It doesn't even really have to be a field. So, right. And that's exactly what we're doing. And so you're on the next slide already. So the point is, say we had an algorithm that given this L tuple now of numbers over this finite field gave us the answer with probability for a random tuple with probability more than, say, 1 minus something inverse linear in the dimension, in the number of bits, L plus 1. Okay. So then I said we can probabilistically compute f hat even in the worst case as follows. So A gets most of the answers right, but when it gets the answers wrong, could do anything. But we could use A to get the answer right almost all the time on every input. And the way we'll do that is we'll pick a random, we have a particular input that we care about. We'll pick a random line through that input. Okay? That line is going to be points, we have a vector of inputs that we care about. That line is all going to be points of the z that we care about plus x times a random direction. Okay? Where x is going to take, is an element of the field. Or an integer, I should say. Okay. So now, on that line, f hat is a multilinear polynomial. So on that line, f hat restricted to that line is a single variate polynomial in x that's degree at most L plus 1. That's a degree at most L, I should say. Okay? Now, if we evaluate that polynomial at L plus 1 points, say x equals 1, 2, 3 up to L plus 1, then we have enough information to interpolate that polynomial and know what it is at 0, which is exactly the point that we care about. Okay. So what's the now we try it at x equals 1 up through L plus 1. Okay? Each of those points individually is uniformly distributed because we picked A at random. So that means the probability that one of our queries is answered incorrectly is at most L plus 1 over 3L plus 1, or a third. So whatever we start with probability 2/3 over choice of the vector A, we get the right answer using this method. And then we can repeat it and take the majority answer to get certainty almost certainly. Okay? So that's how we go from an average case to the worst case. Let me see. So what are we really doing here? Okay. Really, it's the same situation we had before. We're really using, I said Reed-Solomon code, but I guess it really is a Reed-Muller code, because Reed-Solomon would be higher degree interpolation. Okay, Reed-Solomon. But we're taking F. The multilinear extension is an error-correcting code of F. Okay, and then the adversary that can get the answer, that gets the answer right most of the time, but not all the time, you can think of as a corrupted version of that code word. Okay? And what we've shown how to do is take that corrupted version of the code word and exactly recover the message that we had intended. Okay? So, and we do this again, not even reading the whole code word, but just reading it in random places. So what we get is what we're using is that this Reed-Muller code is locally, in this case, uniquely decodable. Okay? And again, any locally uniquely decodable code could be used in place of this multilinear extension in this part, as long as it's efficiently computable. Here, efficiently, it's kind of interesting. In decoding, we have to only make a small number of queries, but in encoding here, we're allowed an arbitrary polynomial time encoding using the whole truth table of the function. And it'll turn, so one thing that you have to say is, like, can we do this? We know how to do this in different complexity classes, like polynomial space or exponential time, or even Sharp-P for those people who know what Sharp-P is. Okay? But we don't know how to do this in the polynomial time hierarchy. And one digression for the complexity theorists in the room is that, well, since the sensitivity of a code has to be high, you change one bit of the message, the code has to change in many places. And any kind of polynomial hierarchy construction would be really a constant depth, unbounded Fanon circuit in the bits of F. It cannot have high average sensitivity. So that's one reason why we can do this for higher complexity classes above the polynomial time hierarchy, but we can't use this technique within the polynomial time hierarchy. So the end digression for complexity theorists and back to a general audience. Okay. So, okay. So, okay. So what's really going on in that step is we're encoding the f hat is a locally decodable code of f. Okay. So then, but f hat isn't, is somewhat random looking in that it's hard to compute all the time, but it's not really random looking. So how do we make it into a function that's hard to even guess with significant advantage? Okay. So this step is hardness amplification. Okay. The most the earliest and still one of the best ways of doing it is simply to take multiple copies of your function f and on independent inputs, and then sort of glue them together with a construction, for example, the parity function. Okay? And it's kind of intuitively obvious, but actually non-trivial to prove. Let me say, this is something I've been proving for 20 years or so. Every few years I come up with a better proof. Better, meaning I like it then. But intuitively, if the original function is hard some delta fraction of the time, then sort of you hit, each time you sort of hit that hard region with probability delta, and so your probability of guessing the parity of all of them drops, the advantage drops exponentially in like 1 minus delta to the number of copies. Okay. Okay. And if you can again think of hardness amplification in the language of error correcting codes, and what you're note that here the new function we're constructing is polynomial time computable in the old function. So this really isn't a good error correcting code in itself, but what we're saying sort of, if you combine it with, if you start with an error correcting code and compose this parity, this constant size parity operation on top of that code, you get another code. And this other code is if the original code is unique decodable from distance delta, this new code will be list decodable from distance a half minus epsilon, where epsilon and delta have the same relationship as in the hardness argument. So it's a hardness amplification you can interpret as a code boosting method, and in fact it was when we started looking at it in this way, we saw that it actually had been used in the coding community implicitly in these papers of Alone, Brook, and all. Like that was from the late 80s, something, I think. Or okay. So I said all of that just gives us one bit of randomness, and we have to get a lot of different bits of randomness from it. So the last step is sort of the most innovative. But it's also very simple. Okay? You start with a combinatorial object called a design. And what all a design is it's subsets of numbers from 1 to capital L, so capital L objects. Each set is size little l, and the intersection of two elements of the design is small. Okay? Now, if capital L is, say, little l squared, you pick two random sets from of size L. They probably intersect in one place or less. Okay? So you can have the if you let t be log n, you can pick exponentially many sets, and with very high probability, none of them intersect more than t places. So a random collection of sets is going to be a pretty good design. Okay? But they're also relatively simple deterministic constructions of good designs with the same properties that are in their paper. Okay, so what we're going to do is let our new seed size be capital L, and where little l is the input size to our predicate. Okay? And for each of these very large numbers of sets, we're going to pick capital L random bits, and then use the bits in each of these sets in our design to define a new input x sub I. So the first set, we look at the bits restricted to that set, call it x1. Second set, we look at the bits in x2 in that set and call it x2 and so on. And that's all we do. Okay? And that defines x1 up through xn, and then we apply the hard predicate to each of these bits. Now, individually, each of these strings is random, so h of xi is going to be hard to compute, guess more than a fair coin flip, but we need something stronger. We need that they're random even collectively, which is equivalent to saying, even if you know all but one, you still can't guess that one with significantly good probability. So this is where the computational independence comes in. We want to say that if you could guess h of xi knowing h of xj for each j not equal to I, then with just a little bit more work, a little bit more size circuits, you could compute h of xi by itself. So the idea is, let's randomly fix all the bits outside of Si. That doesn't completely determine all the xj's, but since Sj only intersects Si in t at most t places, it determines xj up to, there are only 2 to the t possible values for xj. So say that we get the values of h for each of these 2 to the t inputs. That's not a huge amount of advice. We can hardwire that into our circuit if t is small. Okay, so the overhead is 2 to the t times n. Okay, so, and t is about log n. So, okay, so that's still polynomial overhead. Okay, so then, if we've got a predictor for h of xi given all these other bits, now we can just say, given the tuple xj, we just look up on the table which xj we're talking about, use that bit as the help bit for our predictor, and now we can, and now we've got a predictor that that computes all the help bits rather than being told them. And so just given xi outputs h of xi with the same advantage as the one that was told h of xj. Okay. So okay. Okay, so if we combine these three steps, okay, what have we done? I probably should have. Okay. So what we do is we start with an input size that's hard enough, so where the function is hard enough, we have an algorithm that's running in time t that we want to de-randomize. We pick the input size to f so that no circuit of size like t to the fourth or something like this can predict our circuit, can predict our function in the worst case. Then each of these steps, we lose some polynomial in t. We get at the end, we get a pseudo-random generator that's using a little bit more seed size, okay, and is outputting t random bits that still in time t can't be distinguished from t pseudo-random bits that in time t can't be distinguished from random. Then if we use them in our randomized algorithm, it will produce the same distribution since the algorithm can't distinguish, doesn't have enough time to distinguish, it'll produce the same outputs on each input. Same output distribution. And so then we can do, since we have the input size is very small compared to t, we can do exhaustive search over all inputs to our function, to our generator, and try the algorithm on each one, and that gives the de-randomization. Okay. So sort of the harder our function is, the smaller inputs we need to start with, and so the more efficient this de-randomized algorithm will be. Okay. So that's the outline for how we get de-randomization of algorithms based on worst-case hard functions in X. So there's a very interesting connection between these hardness to randomness results and the combinatorial object extractor that I was talking about in the first half of the talk, which is an observation due to Trevisan. Okay. So before, we were using extractors to design pseudorandom generators. Trevisan says, wait a minute, you've got this construction of a pseudorandom generator, it's really an extractor. And turned it around and showed how to make efficient extractors based on the constructions of pseudorandom generators. Okay. Now, in order for this to work, it wasn't based on one particular pseudorandom generator. It was based on the fact that we had a black box construction that took any hard function into a pseudorandom generator. Okay. So the contrapositive is you have a way to map functions to generators, okay, so that if you've got a distinguisher for the generator, that distinguisher gives you a way of computing the function. But there can't a small circuit to compute the function. So, and that small circuit just uses the distinguisher as an oracle. Okay? So in particular, there can't be very many functions that for any particular distinguisher, there can't be very many functions that where the generator doesn't fool the distinguisher. Okay? The contrapositive is if your function is being selected one of a large number of functions, i.e. is coming from a flawed source with many bits of entropy, then there can't, for any fixed test, the output of your generator based on that function is going to pass that test almost certainly. And so that proves that if the function is coming from a source with high entropy, the generator looks random almost certainly. Okay. And the seed for the so the input to the extractor is the function. The seed for the extractor is the seed of the generator, which is much smaller than the description of the function. Okay. And if you look at what this gives you in terms of the actual, if you take the BFNW construction and you just look at it as an extractor construction, what it ends up being is you take some list decodable error correcting code from a half minus epsilon error. That's combining the first two steps. Okay. And actually, it doesn't even have to be locally list decodable or even efficiently list decodable, because the property we want from this extractor is just a combinatorial property. So there just has to exist in potentially, there just can't be too many strings that map to very close to each other. Okay. And then you take your message and you encode it with this list decode. You take your input from the flawed random source, you think of it as a message, and you encode it with this list decodable code. Okay. Now, so far you haven't used your seed at all. It's been completely deterministic. So how do you use your seed? Okay. You use your seed to define bit positions xi using the design method. Okay. So use the designs, go from a small random string to this tuple of inputs to your function x1 through xn. Instead of inputs to your function, you think of these as bit positions in the code word. And you just select those bit positions and you output that tuple of bit positions. And that's your extractor. So if you use this method, you can combine any list decodable code and any design to get a good extractor. And here, unlike the crude version that we had in the Hill paper, the seed size is going to be very small compared to the input size. Okay. Okay. So we managed to de-randomize algorithms based just on a worst-case hardness, which we couldn't do for cryptography. But we still have this non-uniform hardness. Is it possible that we could have de-randomization, as I said, not using only a uniform hypothesis as far as the pseudorandom generator, or could we do de-randomization without using a pseudorandom, any kind of hardness assumption at all? Why do we need hardness assumptions in order to do de-randomization, and why should they be non-uniform hardness assumptions? I'm not going to be able to sketch the argument, but let me just tell you two facts that say that in some sense we can't get around using some kind of hardness assumption. Okay? And in fact, the de-randomization question is intimately linked with one of the other big open problems in complexity, proving circuit lower bounds for explicit functions. Okay. So the first result is by myself, Valentin Kabinets, and Avi Wigderson. What we show is that if promised BPP were decidable, remember promised BPP is the probabilistic algorithms that are sometimes ambiguous, and you're allowed to solve them to do either way when they're ambiguous. Okay. That implies that non-deterministic exponential time has problems with superpolynomial circuits. Okay? So if exponential time requires superpolynomial circuits, then we can de-randomize. If we can de-randomize, then non-deterministic exponential time has superpolynomial size circuits. If only we could remove that n. Okay. We'd have an if and only if. But it does show that either way, it's a major open problem to prove a circuit lower bound, even for a function in non-deterministic exponential time. And it shows that progress in circuit lower bounds is linked to progress in de-randomization. Okay. The other result along these lines, okay, is maybe more is actually relatively easy from the first result, but is maybe even more surprising. So he said there were like a number of classical probabilistic algorithms that people came up with in the 70s. I think the best known is primality, and then the second best known was this polynomial identity testing. We de-randomized primality. Can we just de-randomize polynomial identity testing? This is much, this seems like a much weaker goal than de-randomizing every algorithm in BPP or every algorithm in promised BPP. Can we just de-randomize this one? And we show that based on the first result, if you could de-randomize even this one algorithm, then you either prove a Boolean circuit lower bound for non-deterministic exponential time like in the first one, or you prove that the permanent requires superpolynomial algebraic circuits. Okay? Circuits with addition and multiplication gates, sort of like in the definition of polynomial identity testing's input. And that's also a major open problem in circuit complexity. So you can't even de-randomize this one algorithm without proving some kind of lower bound. Okay. So I'm going, unless people have objections, it looks like I'm going to finish ahead of schedule. So what do we know about de-randomizing algorithms? Well, almost certainly, I said it would be very surprising if there were a probabilistic algorithm that we couldn't de-randomize, that really wasn't de-randomizable at all. But on the other hand, even proving that you can de-randomize a particular algorithm, like polynomial identity testing, requires us to prove circuit lower bounds. Okay. So to prove that we can de-randomize without assumptions seems like a major problem. So sort of tantalizing, we really know the answer, but we also know why we can't prove it. Okay? And then the other conclusion I want you to, that I think should be clear, is that studying pseudo-random generators is a really interesting question in and of itself, but it also leads to really interesting and deep connections with combinatorics, and in particular, questions about constructing combinatorial objects with pseudorandom properties. And the examples we gave were things like extractors, codes, and designs, but there are many other connections. Sure, we have 45 minutes for questions.
So
Yes?
in
Yeah, so,
Maybe you should repeat the question.
so,
No, so how do you select the designs? Actually, it's not a design, but you're talking about 16-bit codes. The design is the intersection is fixed. But it doesn't matter. I mean, how do you select the design?
so Avi called it a design, not me, but,
Anyway, how do you select the designs?
so, okay. Here's a very simple way of selecting the designs if capital L is little l squared. Okay. You look at degree t polynomials. So you fix a field of size little l, okay, or make L a prime or some little l a prime. Okay. And you look at all polynomials of degree t or less in that field and look at the graph of those polynomials. So L squared you think of as the set of points of pairs in the field, and then each polynomial, the graph of each polynomial selects L of these points. Okay. Now, the fact that the intersections are of size at most t just is that two polynomials can agree, two degree t polynomials can agree on at most t points. Okay. So, so then you have to say, well, how big is n? So you have to count the number of degree t polynomials, but you have basically t degrees of freedom as long as t is small compared to L, and each one is, think of the coordinates. Each one you can select independently. So you have about L to the t. N can be up to L to the t, as long as t is not bigger than L. Yeah. So that's on one extreme where you allow capital L to be a polynomial in little l. And there's another construction if capital L needs to be linear in little l, which is somewhat more involved. Or somewhat, it's a construction, but it's not really a construction. It's a very non-constructive construction. They kind of cheat. Yes?
So the conclusion was that we are stuck. We know the answer, but we also know why we
Okay.
can't move it. So what do you predict is the next breakthrough in the de-randomization?
Okay, well, why don't we just prove it? Okay, so the point is, yeah, one way to say we're stuck, I shouldn't be pessimistic. What I should say is, this gives us a great opportunity to push forward the field of de-randomization and of circuit complexity simultaneously. There are already some very interesting results, say by Agrawal, who shows that if you could prove, say, even give a de-randomization for circuits of depth 4 in polynomial time, you'd get a super polynomial circuit lower bound. And we know how to, and on the other hand, people have been working on de-randomizing depth 3 formulas. So all we have to do is increase the depth by 1, and we prove circuit lower bounds.
More questions?
Yeah.
So you said it's a weakest, like if you do randomized algorithms for time t, you need the assumption that hard functions for time polynomial t.
That's right.
But what is the weakest assumption you could make? Give t to 1 plus epsilon?
I see. So usually what okay, so the existing constructions, there are like 4 or 5 places where you lose a factor of where you go from security S to security square root of S. So right now in the existing constructions, we have to overshoot t by some fairly large polynomial amount. Okay, so we have to pick L so that the function of size on L bits is not just hard for size t, but hard for size t to the 8th or something like this. Okay, and no one's optimized that. It would be at least technically interesting if you could bring that down something closer to t. But I don't know how hard people have worked on it. And I'm also not quite sure if I answered your question.
All right, thanks.